Hello. Thanks everyone for coming here. It's quite late in the afternoon already, and I guess everyone gathering here kind of heard about continuous application or field schedule already. So I'm gonna talk about some interesting pattern I've been using inside my company, and hopefully it can inspire some thinking around this community. First of all, let me do a quick introduction so I can fill up some background information. I'm currently a software engineer in Groupon in a team called Behavior Modeling. So as our team icon indicates, we're fighting hackers. We're trying to find malicious activities according to users' behavior on our website. So basically, we're building a very strong log stream processing engines in order to fight malicious activities. So due to the size of Groupon, it's kind of middle size, not too big or not too small. We have to use all the distributed data tools that is well known by everybody, Kafka, Storm, and Spark on Yarn. However, we're deploying on in-house hardware, so unlike Amazon EC3, we have to file a report in order to get physical hardware shipped into our data center and installed. So expanding resource is less ideal an option for us. We have to utilize all our existing resource before we call for new hardware, because typically we're going to wait for about a quarter to arrive. So this actually inspired my research today, and I'm going to share is, are you always utilizing every course you have in your application, and then how to do that? So I need to set up clarify some glossary here, because Spark usually have confusion, like a lot of confusions by using the same glossary. The application I'm talking here about today is the application created by a Spark submit. Basically, it's a jar running on your Spark driver node. And then the job I'm talking about today is a group of tasks that is submitted inside your Spark context. So it's the unit of work to be submitted into the Spark context you have just created in the application. And the task that I'm talking about is the task you're seeing inside the job that you're not aware of when you're writing the job, when you're writing your application, your Scala code, but they are the unit of work to be scheduled inside your application. So job is the unit of the work to be submitted, and task is the unit of work to be scheduled. And next, we're going to talk about scheduler. Scheduler is determining which job can be executed given all the concurrently submitted jobs. It has two modes. FIFO stands for first in, first out, and fair. And you can update spark.scheduler.mode to make a choice between them. The default one is FIFO. And a fair scheduler can have multiple job pools to accept jobs. In this case, this actually introduced another concept called job pool scheduling mode, and it has the same name as well, FIFO and fair. But this FIFO and fair are actually a part of config of your fair scheduler. So they are not as important as the fair scheduler itself. I'm going to wipe it out from my slide today. I'm going to focus on scheduler mentioned above. Okay, what exactly does a scheduler do? Scheduler will determine who can use the resource. But you can do a lot of tweaking to the schedulers in order to figure out how to maximize your resource utilization. In which case, it will reduce your total execution time. The execution time is actually the time between your first task being executed and the last task being finished. It doesn't include the time you wait for your Spark context to be initialized. Secondly, you can improve your task locality, which will reduce your total CPU seconds. So this is separate from total execution time. You could be doing a thread.sleep for 3 seconds on your Spark driver node, which will increase your total execution time by 3 seconds. But that doesn't increase your total CPU seconds. So total CPU seconds actually measuring how many time you have spent doing the actual work. Right. And does the scheduler work all the time? My answer is no. Actually, a scheduler is working only when you have more than one job submitted to Spark context. What does that really mean? Does that mean I just keep writing the code and I'm submitting multiple jobs to Spark context? No. Actually, expression like that, I'm using Scala, so this is a Scala expression to submit 24 jobs. Expression like that actually is sequentially submitting your job to a Spark context. So what I'm doing here is I'm creating an array with 24 elements, and then for each element, I'm going to read a file from the file system and count it so it triggers a Spark job. The reason why I'm saying that is if you look at some visualization about how cluster uses your resource, it's quite obvious that you are not even maxing out your cluster. So I'm running this job on my production cluster. I'm reading 24 files. Each file is around 500 megabytes. And according to Yang's default settings, you're going to have 128 megabytes partitions by 4. So that's a total about 12 gigabytes of content. And then I'm running them with 8 core settings, 8 executor, 1 core for each executor, so I can differentiate which executor has a better locality than the other one. The execution is taking actually 110 seconds. Do you feel like it's fast or slow? I'm thinking it's pretty slow. And let's look at visualization about this one. This graph was created by a tool called Sparklint that I have written and open source last year at Spark Summit Europe. Basically, this is trying to create an error graph to show how your resource is being used inside your Spark context. It's feeding from the Spark event log. So the gray area is actually the idle cores. Since I have allocated 8 cores, during the majority of this application running, I haven't even used 4 cores of my application. The color part with the yellow and orange and red on it actually indicates the locality of a job which is reported by Spark. So the yellow means you're running a task at node local level, and the orange means rack local. If you're not familiar with this concept, node local means your data and the code is almost existing on the same machine. And then rack local means you have to do a network transmission in order to transmit the data to your code, or vice versa. And any means you have to transmit your data across multiple network switches in order to arrive at its final destination. And obviously, node local is more ideal than rack local than any. But in our case, because I'm reading from Yang, I have no control about initial locality. So it's kind of given to me. But anyway, the point is you're seeing 20 spikes on the graph. That means your job are sequentially executed. Think about it, it's like you're driving your car on like Highway 101 right now, trying to reach San Jose, and you have to brake and start and brake and start and brake and start. Can we make it better? Let's pay attention to some important stats. First of all, you have used 11% of the total CPU allocated to you by Yang. And then that equals to 99 seconds of CPU time. So these are the things we can try to attack right now. What if we submit our job in parallel? So there are multiple things you do. Submitting your job in parallel means you are submitting multiple Spark jobs on different threads on your Spark master node. This actually doesn't speed up your calculation. It simply makes your job submission happens in parallel. And the common technique are like quite mature already. Java's runnable, Python's threading, Scala's future. In Scala, you can actually, without using future, you can actually use something called parallel collection, which gives you a very primitive way of implementing that. And also there are libraries like Scala Z and MonoX, which provide some wrapper around it. But after all, this is the simplest version, 4 characters more, and you get parallel submissions. Want to see how that runs? It's actually finishing in 22 seconds. So it's dramatically different from the example I gave you before. It's like you are now driving on Highway 101 at midnight, and you can go to 70 miles per hour or 80 miles per hour, if only there's no cop stopping you. Can we do it even better? Have you noticed anything different from this graph from the example I'm showing before? So obviously, you're seeing more red areas here, which indicates any locality. And there's a proof over here. We have reduced our execution time from 110 seconds to 22 seconds. However, our CPU seconds has increased from 99 seconds to 144 seconds. That's almost about a 45% increase. What does that mean? That means like executing your job in any locality is going to take longer than running in rack local or node local locality. So we can try to improve that as well. But we want to keep this trend going on. We want to see this 100% utilization period to happen more and more often. So remember I'm saying the difference between FIFO and fair scheduler. FIFO scheduler is trying to schedule a task that was submitted earlier, even if just one millisecond earlier, and even if it has a worse locality than the job that is immediately next to it. So we'll try fair scheduler to see if it can improve our localities, because fair scheduler tend to yield resource to those who have the better locality unless they have been waiting in the queue for more than a configurable time, which is spark.locality.wait. So turning on is simple. Provide a configuration in your Spark submit without changing your code. You can get that instantaneously. And the code is still the same. You do a range and do a par, and then for each one you read the file. What it looks like, wow, it's like the red part simply went away. Now, not only you're driving at 80 miles per hour, but also you don't even have a slow truck in front of you, so you don't need to go around and pass him. The stats are, it's using 15 seconds right now instead of 22. And the CPU seconds is a record low 88 seconds. That's almost representing the minimum time you can spend in order to read a job. Think about it, we have 8 cores, 88 divided by 8, it's 11 seconds. So we still have room to increase if we boost our core utilization to near 100%. So what can we do right now? What can we do right now? Have you paid attention to the gap on the right near the end of the execution? The gap is around 3 seconds. It's about 3 seconds width. So this is not a magic number. This is actually the default value of spark.locality.wait. So if you do nothing about changing your Spark locality settings, you're going to see these kind of things happen quite often. So we know what's causing the problem. Let's tweak that. Because we have spent 88 seconds reading 96 partitions, that means our average cost of reading one partition is about 1 second. So I'm putting a magic number here, 1 second, as an indication about how long you should wait until you check for the next locality. Actually, this has been proven pretty difficult in your real production job because it's very difficult to find the best number of your locality settings because your job tend to vary a lot. You can be reading kilobytes at the very beginning, and your task can be reading gigabytes at the like in the other part of the application. And it's so difficult to find locality settings that is perfect for your job. But anyway, let's see the impact of it. That's the most beautiful graph I've ever seen so far in my demo. So we have almost 100% utilization, actually 97%, with a little red area on it, but they don't impact your total execution time a lot because like if you're not running these jobs in any locality, you're going to waste them. So we have a record low 12 seconds execution time, and then the total CPU seconds has increased like marginally from 88 seconds to 93 seconds. We can actually ignore that. And this 12 seconds is almost identical to my prediction saying we can finish that in 11 seconds if everything works fine. So this is a quick cheat sheet about different mechanism over here. First of all, doing code change to submit your job sequentially versus submit job in parallel can give you a better customer utilization if you know that your customer is not being utilized that much. In turns, by improving your customer utilization, it's going to cut off your execution time by a lot. And then using the fair scheduler, which is not a code change, it's a config change, you can actually tweak your localities so you can further optimize your job by tweaking the parameters instead of making a code change. And then keep in mind, the sequential behavior is kind of default in Spark Shell because you're typing lines after lines. This is like you have only one way to interact with the computer. And the FIFO scheduler and parallel submission is almost like the behavior in Jupyter Network or a Jupyter Notebook or Zeppelin Notebook because you can do multiple things in the same notebook. So you are able to submit multiple jobs naturally. In this case, we actually think like fair scheduler can always be better than a FIFO scheduler because it doesn't really make any difference if you have one job running. But when there are two jobs running, FIFO is always going to have a better locality than fair scheduler is always going to have a better locality than FIFO scheduler. So we have talked a lot about fair scheduler so far. What about continuous application? So continuous applications is kind of like a new world, a new concept invented last year that you can do multiple things. Like instead of saying I'm running a streaming job, I'm running a batch job, you just run an app and the app will do a lot of stuff. So I'm trying to figure out what that really means. So think about the most common workload in your cluster so far. The top one is kind of like reading data. So again, the vertical axis is how many cores you are using, and then the horizontal axis is what is the time axis. So if we're reading data and do it perfectly, you're gonna have a shape like that, like a square, and then you like write it to an external source, or you save it to a database, something like that. And if you're executing your model, because your model is going to be complex, they're gonna run it over time. And then because your model or your logic is going to be repeated, submitted, so you need to, like if you look at multiple applications and think about they are running as one application, their usage graph will like the orange part of it. And typically you're gonna schedule them in a cron tab or a script or whatever, but you're going to have multiple jobs submitted at different times with the same purpose. So if something goes wild, for example, you're scheduling a job at 5 minutes interval, and then one job happened to use 10 minutes, and then at some time in your system, you're gonna see 2 jobs with the exact same name running with similar content. And actually, you probably don't even care about the job happened before, because now we have a new job with a little bit more data that's gonna produce a better prediction on the data set we have. So that is to say, submitting your job one by one in different applications is actually not an optimal solution to do that. Oh, sorry. Let me go back. And then stream process is a graph that everybody can expect. You have a streaming job that is long running, and then you have into batch and batch and batch. You're gonna see spikes and after spikes. And for reporting, it's actually even more interesting. Reporting jobs are those triggered on demand, so you don't want to execute it at a fixed time. Actually, whenever there's like for example, in my case, whenever there's a hacker attacking, or whenever there's a fraud case happening, we want to do some ad hoc analysis of data. So you have to boot up a Spark context, wait for 20 seconds or 120 seconds, depending on how your cluster is configured, and then run a query and then kill a job. So the feedback loop is actually longer than it should be. And the workload is, the payload of your reporting is actually similar to reporting data as well. What if we merge them together? We can actually fix them all inside one container and sharing resources with each other. Think about it. If your streaming application has finished the processing for the current batch, let's say your batch interval 5 seconds, and you have written a great algorithm that finished calculation in 1 second, what are you gonna do in the next 4 seconds? They're being wasted. But you can actually use them to execute your models. You can use them to execute your ad hoc queries as well on the same data set you have just processed. So this is actually a very interesting comparison between running multiple applications on the same feature versus running one application on the same feature. So you're gonna be able to pass the RDD reference around instead of saving your RDD to a file by writing a serialization function, and then deserialize that again for another application. Or in some cases, you're gonna pipe it to Kafka and read it from Kafka. You're gonna pipe it to in-memory storage and read it from. Anyway, you have an intermediate step, but now I have a RDD reference to pass around. Resource allocation. Think about it in the case we have 4 applications. How many cores are you going to allocate to them? If your traffic is kind of smooth, you can figure out the best core to allocate them. But in reality, for example, in e-commerce, when you send email to a customer, we tend to open email at 10 o'clock, so you're gonna have a spike anyway. Most of the time, you're gonna optimize for worse situations. So instead of 4 cores that is good enough for 99% of your use case, you tend to allocate 8 cores in case you have a spike in your traffic. So they are wasted most of the time. And you have 4 applications to tune. But if you're doing one application, you have only one problem, which is how many cores do I fit for my entire feature. It's almost similar to when you are doing when you try to write a backend server, you need to figure out how many instances do I need based on the amount of traffic I'm going to serve. And then job scheduling becomes way easier as well, because now we have one application, you have a programming language to schedule them instead of writing a clumsy cron tab, or in other case you have to write Uzi XML or other kind of stuff that doesn't have the context about what the last execution result is. So I figured out job scheduling might be easier in continuous application as well. So here are a series graph about how I'm operating my hybrid application at Groupon. So this is not like the stream process you have saw before. So let me take some time to explain the graph. First of all, we have a stream that contains all the information we care about in our application. And we have two algorithms to aggregate them. For example, aggregate all the clicks by IP address and aggregate all the user emails by IP address. And then we have a model that looks at the clicks and emails from the user in order to figure out who are fraudster, who are not. So we have a model that depends on two views of the same stream. My approach is keep two maps in your data structure on your Spark driver node. And then whenever a stream has been received, you're going to take it off the thread that is processing the stream reading and push them into another thread that does the aggregation for you. So in my case, you will have, first of all, your historical state from HDFS for each data series. And then you're going to have the in-memory result of each batch of these data series. And they can happen at different pace. And then your batch will keep coming, and then they will keep queuing up. And then the one has been processed already will be in green. The one that is currently being processed will be in blue. And then the one that is pending is in red. Yellow is for executing jobs. And this is time 2.5 right now. I have triggered model execution using the data available at this moment. Now we have moved to time 3.1, where when a new batch has arrived, but the previous batch processing is still going. This is the case for Series A. And for Series B, since it has finished the processing already, it's going to start processing the new data immediately. Now we have 3 jobs running in parallel in our Spark application. After Series A has been working on batch 2, they're going to start working on batch 3's data as well. And at this time, we have figured out we got new data in our data sources. So we're going to trigger a new model execution as well in our model execution logic pipeline. But they are not evaluated at this moment. They are pushed into a queue, so whenever the current process finished, it will be triggered immediately. So this is almost like a single-threaded pool that you are blocking executing your model on that pool, on that queue. And then at 4.3, the model is still going on, and we're receiving new batches. So the model processing thread is still being blocked because it's waiting for the current model process to finish. But the stream processing thread can happen in parallel in order to process the new data we have received in second 4. And at 4.6, we have finished our job. So now we're going to take the next model that is in the queue and execute that. Let me rewind a few slides and take a look at the timestamp on the execution job that is pending. It was 3.6 before, and then it was 4.3 at this moment. That means like we're going to cancel a job that is having less data than the job we have submitted recently, because in my application logic, we're going to make predictions only on more data rather than less data. I mean, like having more application will lead you to a reverse action instead of positive actions. So this is our logic, is like we want to cancel the job that is being outdated because we always want to use the latest data available to me at that moment. So here's our logic. When this model triggered at 4.3, we're going to use the data we have seen already as one part of the input, and the data we haven't seen as the delta as another part of input. So we can either use a union of them to get entire, for example, 24 hours of data, or we can do a left join on them in order to figure out who has visited our site during this period between the last model has finished and the current model has triggered. Anyway, so this is a process approximately like describing what are we doing in my company in order to combine model execution, stream processing in the same container and to achieve a good result. So overall, the practice are decouple stream processing from batch processing, which will give you a final control about how many data, what's the resolution you want, and what's the SLA you're going to guarantee. Secondly, I want to emphasize the tuning for the streaming part because I can push most of the tasks that involve interaction with other data source into the batch processing part. So I can tune for my streaming part only for the in-memory computation. And that's the part I'm going to guarantee is my stream processing is always going to finish within the stream batch interval. And then for anything that I can't control, they will be handled to another thread and then executed on their own cycle. And the third one is I want to execute only the latest batch invocation. This is actually like problem specific. You might not have the same assumptions that I have here, but if this is the case, you will be better off by clearing all the accumulated batch and execute only the latest one. And then your reporting and query can be happening on-site in the same Spark context by exposing a RESTful endpoint on your Spark driver node, or you can design other kind of smart interaction with a Spark context. And then you can actually assign that to another scheduler pool which has a lower weight, so they will be triggered only when other important jobs has finished. Or you can find the best ratio of them as well. Like there's a lot of knobs to tweak in terms of fair scheduler settings. And this is a screenshot about our jobs running in production at this moment. Like we have multiple pipelines. They have been tagged about what's the purpose and which pool they have been submitted to. And also you can see the resource distributed like according to their needs and according to their pool settings among each other. All right, and the summary slides is kind of messy, but it covers all the idea I have talked about today. First of all, like share your data via RDD, and then try to decouple your stream processing for your batch processing. And then when doing your app submissions, try to use fair scheduler. It might just cut your execution time by 90%. And try to turn off dynamic allocation, which I found is not useful for a long-running job because the number of tasks doesn't really represent the size of the problem you're trying to solve. And another thinking is you can actually turn your batch job into a long-running job as well. Think about batch job as ad-hoc queries. You can trigger these ad-hoc queries inside your own application to mimic a cron tab with Scala or Java or Python that is more comfortable to work with. And then in your job bootstrapping, try to use these Spark context debugging methods in order to tag them and help you to identify who should be submitted to which pool. Something like that. There's too much content over here. And you will be able to see the slides as well if you're interested in more content. And if you want to reach out to me, my email is rxue@groupon.com. And the tool I'm using is Groupon/Sparkling. You'll be able to find that on GitHub as well. And thank you, everyone, for listening so far.
Thank you, Robert.
We've got a couple of minutes. Actually, I accidentally started this presentation a bit early, so we have a few minutes. So if you have any questions, please feel free to go to either of the mic on either side over there. There's a mic at the end. Do you mind? There's no mic over there.
Hi, my name is Oliver. I'm representing iPass. And so my first question is, I did try to recently use .par, which you initially was showing in the slides. Mm-hmm. And I spoke to Samir, the data lead at Databricks, and he was actually against using .par, mm-hmm. and instead he preferred using the Spark context .parallelize function instead, just because when you go to when you do .par, you basically parallelize over your Scala collection, mm-hmm. instead of going into like Spark parallelize. So do you have a preference over the other, over one or the other?
Yeah, this is actually not doing a par on a data set. It's actually doing a par on your job submission logic. It's all meta processing here. There's no data being involved.
Right. That actually was something that I was following up as well. And then my second question would be, did you ever see any downsides, especially with the executor ID being duplicated when you like run the job multiple times? Because there is an open bug that resurfaced in Spark 2.0 mm-hmm. that wasn't present in like the earlier version of Spark. It came back in 2.0, and then it was supposed to be fixed in Spark 2.2, but I'm still not sure about that.
Yeah, the downside I'm seeing, first of all, like Spark UI is using a lot of resource, especially if you have a lot of jobs running in parallel. The Spark UI is going to consume a lot of resource on your Spark driver node. And that's one of the problems. And secondly, you will have multiple jobs try to access the same block of RDD. So my solution is I'm going to increase the RDD parallelism into 2x. So they have 2 copies around it. So you can have, you are more likely to have a rack local or node local copy instead of any locality. And the third one is if you have a long-running job, because Spark's scheduler doesn't work as Yarn scheduler, it doesn't kill the executor in order to yield resource to those we need it. So if you have a long-running job that's going to run for 5 minutes, they're going to occupy that for 5 minutes. So you have to be aware about like your workload should be similar to each other, so they can utilize the scheduler. So like these are the problem you might encounter as well, and it's related to application nature rather than the mechanism itself, I think. That's my opinion. Yeah.
Go ahead. We'll take one more.
Run into any specific problems, like I guess if the application fails and like restarting it, are there any special things you have to do to get it running again? Since it's all kind of in one thing.
Yeah, it depends. So the everything into one. The one here is not an absolute, is not a dogmatic number. It's actually just like having more related feature into one application. You can still have multiple applications. For example, if you try to implement a lambda architecture, you're still gonna have a persistent layer that is running stably on another application to make sure the data you need to recover your continuous application is gonna be there when it restarts. So you will have less responsibility to make sure your data will be saved to the drive in this continuous application track, because they're doing their best job in terms of running faster or running more efficient. So basically I'm saying it's like you can still have multiple jobs, and each job will have different purpose. Some jobs' purpose is to save the file onto the hard drive. Some jobs' process is to make sure you have the correct counts so you can restart the job. They still need to exist.
Okay, thanks a lot, guys. Give a big hand to Robert.
Thank you.